Hello, dear students. Today, our topic of discussion is Zener Diode. In the last lecture, yesterday, we discussed what is a PN junction diode. What is now you are familiar with the P type semiconductors, N type semiconductors, and how the combination of a P type and N type semiconductor results in a diode, which is sometimes known as PN junction diode. And we discussed the characteristics and especially IV characteristics, and we saw that there is a non-linear relationship between the current and voltage for a diode, and which is also known as non-ohmic device. So we have two types of device, linear and non-linear, or we can say ohmic or non-ohmic. So which follows the Ohm's law are called as ohmic, which don't follow means non-linear. Graph between I and V is known as non-ohmic device. So a diode is a non-linear or non-ohmic device. Now, after discussing and after getting the points, what is a diode, how diode works, and what are the forward bias and reverse bias, now we come to a special kind of diode, Zener diode. You can see a symbol of Zener diode as shown here, and anode and cathode are also shown, means P and N. P means anode and N is cathode. So just like PN junction diode, its symbol is just band in the form of a Z. If you see it in the if you rotate it and see it, you can see a Z. So Z for Zener. So a Zener diode is a reverse biased PN junction diode, and the condition is it should be heavily doped. So first thing is that it should be reverse biased, and second thing is that it should be heavily doped. Heavily doped means the doping which is used to create P type or N type semiconductor, any pentavalent or trivalent doping, the concentration of dopant atoms must be very very high, so that we have large number of charge carriers in any either set of semiconductor. Means in P type we will have much more holes, and in N type we will have too many electrons. Also, because now the concentration of free charge carriers is very high in N type and P type semiconductors, so when both are diffused, when there is no bias, then because of the gradient of the concentration, diffusion occurs. Diffusion, because of the diffusion means movement of charge carriers from one side to another side. So they will the electrons and holes will move from one side to another side, and remember there is no bias applied. So what happens due to this movement? The charge carriers will recombine. So electrons will meet through a hole and it will recombine with that, and a neutral atom will be formed again. So because of this, we have a depletion layer just in the middle of the junction, and this layer is depletion layer, called depletion layer because it is depleted, means empty. It is not having any kind of charge carrier here, no electron or no hole, just the atoms are here, semiconductor atoms. So because when we have a heavily doped PN junction diode, then the depletion layer is very thin. So this kind of situation or the characteristic is used in making Zener diode. And Zener diode works on the phenomena of Zener breakdown. So what happens, I will come here again. Let me show you first this graph. We already discussed this yesterday, the IV characteristic, and just focus on the left side, means the reverse characteristics. For the moment, let me emphasize here how the reverse voltage or the reverse bias results in the reverse current. So forward current is in milliampere and reverse current is in microampere, which is very, very small. So how the increase in voltage, reverse voltage, results in the very small current, which is not increasing, which is just saturated. As you can see, just up to the 5 volt or 4 or 5 volt, the current is not increasing and it is very small. But after that, you can see just near the 5 volt, we have a very sharp increase in the current, which is known as the Zener breakdown. So Zener breakdown, and at that voltage, that which is called a breakdown voltage, now there is no need to increase the voltage. Voltage is constant, but the current is very much increased. This is known as Zener breakdown, and Zener diode works in this phenomena. I will come to this avalanche breakdown later. First, let me come back here in this slide. So the main points are reverse bias, it should be in reverse bias, and this Vz, if breakdown voltage is called Vz, then voltage should be greater than Vz, then only we have a breakdown and the sharp increase in the current. So, and current should be less than Iz maximum. Okay, so Iz minimum and Iz maximum we can identify from this graph. If I zoom it here, so the saturation current is Iz minimum first, and when the breakdown occurs, it is the highest value, Iz maximum. And Vz, you can see here that Vz is not increasing, not changing in both the cases. Vz is constant. So this property is useful in applications, because now the dynamic impedance, if I define here as delta Vz over delta Iz, then you can see it comes out as 0, because now Vz is not changing. So delta Vz is not changing, means there is no change, so it is 0. So this property can be used in regulation, voltage regulation, so which is an important part of the power supplies. So when we will discuss later the rectifiers, then at the end, means the output of the rectifier will need to be regulated, because we should not have a regulation, means no fluctuation. Even if we have a fluctuated voltage and the output of our rectifier, then if you use Zener diode, then we will not have a fluctuations, means it will absorb all the fluctuations and it will give us the constant output or the regulated output. Okay, and now we can discuss the avalanche breakdown or the mechanism of the breakdown. So here I have summarized here Zener breakdown and avalanche breakdown. So the mechanism as well as the difference between these two types of breakdown will be clear. So for Zener breakdown, first let me discuss it. We should have heavily doped and narrow depletion layer. So what happens with that, how we get a very high current? Because due to this narrow depletion layer, now the electric field will be very high through this layer. Because of this very high electric field, this is sufficient to break the covalent bonds and our electron hole pairs are generated. So more number of electron hole pair results in more current. That's why what we have discussed just in the previous slide. And in avalanche breakdown, if you see here, this avalanche breakdown occurs just some means more at higher voltage than the Zener. So what is the mechanism of this avalanche breakdown? For this we have a lightly doped. On the contrary, we have a lightly doped junction. So we have a wide depletion layer, and electric field is not very much strong, so Zener breakdown will not occur, but some other phenomena will occur at some high voltage than the breakdown voltage, Zener breakdown voltage. What happens here? The minority carrier collide with the semiconductor atoms in the depletion region because these are accelerated. Then now the covalent bonds are broken again and the electron hole pairs are generated. So in both the phenomena, more number of electron hole pairs are generated, but the mechanism is different, and in both the cases breakdown occurs. Zener and avalanche both results in very high current with very small change in the voltage. This is the ideal model and characteristic of the Zener diode. So as you can see, we have shown the reverse bias, the reverse voltage and the reverse current. So the ideally what is considered, that Zener diode, the as I defined the impedance, means delta Vz over delta Iz, is there is no change in delta Vz, but there is very high increase in the current, reverse current. So it's 0, means there is no change, but practically it is not the case. The case is different. So practically what happens? Practically you can also see the difference in the equivalent circuit just in the ideal model. As you can see here, we have shown here in the ideal circuit just a diode, 2 electrodes are shown, but here a resistor also shown, which is ZZ, means the impedance. So there is in ideal circuit ZZ is 0, means the impedance, dynamic impedance is 0 in ideal one, but practically we have some. So as you can see clear from this characteristic, again the reverse voltage and reverse current are shown, but now ZZ is the dynamic impedance, again delta Vz by delta Iz. Now there is very small change in delta Vz and very high change in the current. So delta Vz and delta Iz is not 0, but it is very small. So this is the difference in the ideal one and the practical one. So Zener diode is very useful and have the applications mostly in the regulation of the voltage. So even if we have the change, means in the power supply, we have shown here what is the output of power supply. So power supply is used for converting an AC signal to a DC signal. So power supply, output of power supply is a DC voltage, and this DC voltage is fed to the Zener diode, and if the input voltage, means the output of power supply, increases or decreases, in both the cases the output of Zener diode remains constant. This is the property. of a Zener diode in the regulation of voltage. Means it should not give a fluctuation in voltage. So we can use it, the output of Zener we can directly use for the any kind of practical devices or household devices. So this is Zener diode essentially in fit in all the power supplies in the adapters. Here we can see how this regulation works, how Zener diode works. So you can see here this VIN is the output of any kind of rectifier. Now after this VIN is obtained from a rectifier, this VIN is applied to a Zener diode through a resistance R, and RL is the load resistor across which V output is taken, which is V output is the constant, it should remain constant. So it's a simple equation that the total current I is equal to I as Iz plus IL. Here you can see I equal to Iz plus IL distributed in IL and Vz, because Vz is in parallel. One is in the Zener and one is in load. So this simple equation gives us V output equal to VIN minus IR, where I is Iz plus IL. Okay. So we can say R is equal to VIN minus V output over Iz plus IL, or R equal to VIN minus V output over Iz maximum. So ये इक्वेशन है, एंड इससे हम ये देख सकते हैं कि इवन इफ देर इज़ अ चेंज इन इनपुट वोल्टेज VIN चेंज हो जाएगा तो भी हमारा V आउटपुट चेंज नहीं होगा। इस इक्वेशन से, मैं इस इक्वेशन को जूम कर रहा हूँ। अब हमारे पास दो केसेस हैं। फर्स्ट इज़ अगर हमारा V आउटपुट वेरी कर रहा है, मीन्स देयर इज़ अ फ्लक्चुएसन, V आउटपुट कम या ज़्यादा होता है, तो हमारा Iz जो है इस इक्वेशन की लेफ्ट हैंड साइड में अगर चेंज है तो V आउटपुट हमारा आउटपुट है जो कि कांस्टेंट रहना चाहिए। वो कैसे होगा? अगर VIN चेंज भी होता है, अब सपोज VIN बढ़ गया, इंक्रीज हो गया, तो Iz जो होगा वो भी थोड़ा सा बढ़ जाएगा, जेनर करंट बढ़ जाएगा, सो दैट कि उससे सब्ट्रैक्ट हो जाएगी जितनी चीज़ VIN में बढ़ गई थी, जितनी वैल्यू उतनी वहाँ भी बढ़ जाएगी, तो ओवरऑल V आउटपुट कांस्टेंट रहेगा। सिमिलरली VIN कम होगा तो Iz कम हो जाएगा। सो जेनर डायोड ऑटोमेटिकली हमारा उस चेंज को एब्जॉर्ब कर लेगा, उन फ्लक्चुएशंस को। एंड ऐसे ही अगर हमारी करंट चेंज होती है, अगर हमारी लोड करंट मीन्स IL भी चेंज हो जाए, ठीक है, तब भी V आउटपुट चेंज नहीं होगा, बिकॉज IL चेंज होने से Iz फिर से कम या ज़्यादा हो जाएगा। ओवरऑल I इक्वल टू Iz प्लस IL है, वो सेम ही रहेगा। IL ज़्यादा हो जाएगा, लोड करंट ज़्यादा हो जाएगा, तो जेनर कम ले लेगा, तो टोटल करंट सेम ही रहेगा। इस तरीके से जेनर की ये मैकेनिज़्म है कि हमको एक रेगुलेटेड वोल्टेज देता है, तो पावर सप्लाई कंप्लीट हो जाती है यूजिंग द रेक्टिफायर एंड दिस फिल्टर्स एंड रेगुलेटर्स। सो हम ये डिटेल्स आगे पढ़ेंगे, बट आज हमें ये डिस्कस करना था कि जेनर डायोड क्या होता है एंड हाउ डज़ इट वर्क। So I hope it is clear to you, and if you have any question then feel free to ask. Thank you.